In this video, I'm going to discuss the stability of the nucleus. So in order to do this, we need to talk about what the four fundamental forces of physics are. So we've already learned about two of them. There's the electromagnetic force and the gravitational force. And remember, both of those forces look very similar. Their equations are inverse square laws. So the closer the two objects are together, the stronger the force becomes. The other two forces are the weak and the strong force, and these really have to do with the nucleus and the stability of the nucleus. The strong force is the force that holds the nucleus together. So if you think about the electromagnetic force, we have all these protons in the nucleus, which is why the electrons that are outside in shells or in orbitals are attracted to the nucleus, because we know opposites attract. However, protons should repel each other, right? But they're all in this small, dense space of the nucleus. We've got all these positive protons, so why don't they fly away from each other? And the reason is there must be another force that holds them together that is stronger than the electromagnetic force, and we call that the strong force. The weak force is a force that keeps the subatomic particles what they are. So if it's a neutron, it keeps a neutron rather than allowing it to decay or change into a proton or change a proton into a neutron. Both of these forces, the weak and the strong force, only happen when you have a very small, very short range. It's like less than a Fermi. They have to be closer together than the size of a nucleus in order to see these forces. So a nucleus is stable when, in different scenarios based on the size of the nucleus. So if we have a really small nuclei, they're most stable when the n number equals the z number. So if you look on the periodic table, or you're familiar with chemistry, the most common isotope for like oxygen is oxygen 16, one that has 8 protons and 8 neutrons. So the z number and the n number are equal. Or nitrogen, the most common is nitrogen 14, which is 7 neutrons, 7 protons. So for very small nuclei, where z is equal to n is when we have the most stable nucleus, and that's why they're found in nature. This graph down here actually plots all of the most common isotopes. So there's like 100 and so elements on the periodic table, but this plots the 260 most common isotopes of all of the elements. So you can see as you start to get bigger and we have heavier, larger nuclei, that it starts to curve down, and a nucleus is going to be more stable when you have more neutrons than you do protons. So when a nucleus is unstable, it can decay, and we can cause this artificially, but it also happens naturally, and there are 3 types of decay. There's alpha, beta, and gamma, and I'm going to go into each 3 of those specifically. So alpha decay is when an unstable nucleus releases an alpha particle. Essentially what an alpha particle is a helium atom that has a Z number, or a proton, the number of protons that is 2, and it has a mass number of 4. So you start with plutonium here, which has a mass of 94. This isotope, it has a Z number, 94 protons, and a mass of 240. And it's unstable, so it releases a helium. This is actually called transmutation, because as it releases helium, it's changing the number of protons that the nucleus had, and therefore you're transmuting or becoming another element. The mass number and the proton number over here have to be equivalent to what's on the right-hand side. So we've gotten rid of 2 protons. So what would remain would be an element that has 92 protons, which is uranium. Remember that the proton number, the Z number, determines what element you are. Now up top, we've lost a total mass or number of nucleons of 4, so 2 neutrons, 2 protons. So the remaining mass in the nucleus would be 236. So notice that these numbers are equivalent on either side. So that's alpha decay. Now beta decay is a little bit more complicated, and how we discovered it, so I'm going to kind of go through the experimental data on how we discovered it. So we know that what we notice is that neutrons could change into protons. So if a neutron changes into a proton, it has to have a net positive charge. So the nucleus actually throws an electron out of the nucleus of the atom in order to conserve charge, right? Because if you become positive, somehow you got to get rid of some negative stuff if you're originally neutral. Okay? And so the experimental data showed that after an electron was emitted, and this is not like an orbital electron, it's not an electron that's out in the shells, it's like an electron that's created inside of the nucleus. It's different than the electrons in the shells. But what we saw was that when an electron was emitted, that it didn't have energy equivalent to the change in the mass of the atom. So we know that elements do have, electrons do have a little bit of mass, and when that electron leaves, then the mass of that electron should be equivalent to the energy that electron has, because remember Einstein's E equals mc squared. But as it happened, it didn't. So we thought, maybe this is defying the law of conservation of energy or the law of conservation of mass. But instead of believing that we were breaking such profound rules of physics, we went and we said, well, there must be something else that's coming out of the nucleus that is we can't detect. And so if we can't detect it, then it must not have a charge and it must not have a mass. So we called that a neutrino. Now, after we discovered, so that was beta minus decay, but after that we also discovered beta plus decay, so we kind of had to redefine our terms. So if you look here on the bottom, it more in detail goes into what beta plus and beta minus are. Beta minus is when a neutron becomes a proton. So we add a positive charge because the neutron has become a proton, so we've got to throw an electron out. And when we throw the electron out, we know that there also has to be a particle that leaves, that makes up for the amount of energy that is being changed by the amount of mass change due to the electron leaving. So we call that particle an antineutrino. It's an antiparticle. Okay? And if you look over here, this kind of shows it this shows an animation, but this actually shows what it looks like. So you've got carbon 6, and it has a mass of 14. So you're taking a neutron and you're turning it into a proton. So you have a different number of protons, so you become a different element. Now you're nitrogen. Protons and neutrons have the same mass, so you still have the same number of nucleons, right? So you still have 14 nucleons, even though one nucleon has become a different kind of nucleon. And then over here on the right-hand side, we represent the electron as an E with a negative charge and the antineutrino as a V with like a vector hat over the top. Beta plus decay is just the opposite of beta minus. So instead of going from a neutron to a proton, you're actually going from a proton to a neutron. So you can see that we still have 10 nucleons here, but because a proton has become a neutron, we now have a different element. Because a proton has become a neutron, we have to shed some positive charge because we've gone from positive to neutral. So the positive charge that is shed is a positron that is thrown off. And again, we had the energy inequivalency problem, so that is what we call a neutrino. So we kind of had to modify what I explained at the beginning once we realized that both things were happening, not just neutron to proton, but also proton to neutron. So if we look at that here's the formula. You've got carbon, which is 6, and it has 10 nucleons. Well, one of the protons becomes a neutron, so we still have 10 nucleons, but now we only have 5 protons, so we're boron. The neutrino is written with the letter V, and a positron is written like it's an electron, but with a positive charge. So that is beta decay. The last kind of decay is gamma decay. So remember that gamma rays are really high energy photons or high energy electromagnetic waves. And in the case of a gamma decay, essentially what is happening is that the nucleus is, the protons and the neutrons are sort of arranged in the nucleus in some shape, and they can actually change their shape and move into a high energy state. It's sort of like when we looked at the electrons and the arrangement of electrons, of an electron jumping from a low energy state to a high energy state, and then when it fell back down, it released a wavelength of light, right? So we're changing the energy, and then the energy had to be stored somehow. So that's simple. That's similar to what happens in gamma decay. There is no change in the number of nucleons. All we're doing is we're rearranging sort of the orientation of the nucleons to be high energy, and then they fall back down to their normal state, and the energy has to be released somehow, and so it's released in the form of a gamma ray. Now, we can induce this and make this happen by using hadron collider. So this is, or any sort of particle collider, and this is some cool pictures of the hadron collider. So here you can see it's this hollow tube, and that's where they the particles actually travel through. And this is an aerial shot of the collider actually, so you can see how big it is. We're talking about kilometers here, that the particles race around and then they smash into each other on the other side. So we can induce sort of this excited state of the nucleus. If we look here, this shows the form, or what the equation looks like for this kind of reaction. So you have a helium that's in an excited state. So you can see the nucleus here looks a little bit different than the nucleus here. This is a high energy state, so it's absorbed some sort of energy. It's helium, it's got 3 nucleons, it's got 1 proton, and actually it should be 2 protons. I don't know why that's a typo. Maybe this should be hydrogen, but don't worry about that. Essentially what we want to notice here is that you are going from helium, and you're staying helium, but you're moving into a state in which you're lower energy. So somehow that energy needs to be released, and it's released in the form of a gamma particle, which we represent with this Greek letter. Let me just go ahead and change this. This should be a 2, and this should be a 2. Okay, so those are the 3 kinds of decay we've got, and discussing the stability of the nucleus. So we've got alpha, gamma, and beta. In the last video, I am going to then just briefly discuss nuclear fusion and nuclear fission.